Question 9.22. If a sample size of 16 yields an average of 12 with a standard deviation of 3, estimate the 95% confidence interval for the population, assuming a normal distribution. The first thing we need to do is find the confidence interval formula for a population average. If you go to section 9, page 35, you will see that there is a section called Continuous Data Small Samples. Now we're using the small samples because we have 16 samples, and small samples is defined as data less than 30 samples. In that case, we're going to use the t-distribution instead of the normal distribution. And at the end, I'm going to explain why that is. So we need to look up our values for average, standard deviation, sample size, and t alpha over 2. And they go through an example in the book, but we'll walk it through with our data. So next we determine those values. Mu, which looks like a U, that's your average, and that will be 12. Sigma, which will be your standard deviation, is 3. N is sample size, that'll be 16. And now we have to find T alpha over 2. So first thing we need to do is figure out what alpha is. Alpha is basically the risk, which would be the amount of risk you want to take where you don't meet the 100%. So we take 100% minus the confidence interval of 95%, and that leaves 5% remaining for our risk. That's the probability we might be wrong about our confidence interval. That can also be written as 0.05. And if you take alpha divided by 2, then you get 2.5% or 0.025. And we divide by 2 because we want to have an upper and a lower tail. So we're splitting the risk evenly on both sides. Next, we look up the value in the t-distribution table, and we'll look under the column of t of 0.025. And then we'll also need to look up the degrees of freedom. The degrees of freedom is the sample size minus 1. So we'll have 16 minus 1 equals 15 degrees of freedom. If you look at the t-distribution table in section 12, page 8, we have a column in there, t of 0.025. We also have 15 degrees of freedom on the left. Where those two intersect, we see a value of 2.131. That is our t alpha over 2 value. So then we go to our formula of x bar plus or minus t alpha over 2 times s divided by the square root of n. So to determine that x bar, that's the same thing as the average, except it's for the sample. So we're trying to use this confidence interval to predict our population mean or average. All we have is the sample average and the sample standard deviations. So those are the numbers we'll have to plug in. So x bar of our sample is the average of the sample, or 12. S is the sample standard deviation, so we'll use the standard deviation to give us 3. The n equals the same number, 16, and then t alpha over 2 is 2.131. And now it's simply a matter of doing the math on this. So we take 3 divided by square root of 16, which is 4. 3 divided by 4 is 0.75. Multiply that times 2.131. Now we have 12 plus or minus 1.598. We can round that to 1.6 to keep it simple. Now we have 12 plus or minus 1.6. That means we have to do the formula of 12 plus 1.6 and 12 minus 1.6. And if you do those, you get 13.6 and 10.4. That is your confidence interval, your 95% confidence interval of this population average. And if we go back to the original problem, now we find the answer that best matches that. And we see A is an exact match, 10.4 to 13.6. Now the other question came up is why the t-distribution instead of a normal distribution? Mainly because we don't have as many data points yet. Once you get up to about 30, 40, 50 data points, you start to see most of the variation you're going to see in your data. Now it's just refining the details. When you have less than 30 data points, you might not have seen all the variation in the edges of that distribution. So what the t-distribution does is the less data points you have, the wider the distribution is from the normal distribution. So it's like a normal distribution except wider. The wider it is, the less degrees of freedom you have. which means the less samples you have. So let's take a look at this diagram. The red is the normal distribution shape, and that's for samples over 30. If we go to 20 degrees of freedom, which would be essentially 21 samples, you can see that the curve gets a little wider. And that's to account for the fact that you probably need another 10 or so more data points. So it's going to widen the curve out to say there's probably some data points you haven't seen yet. And then if we look at the blue line for degrees of freedom of 10, you can see it's even wider than the green line because there's even less data points that we can see. And so they are basically saying you're going to see a lot more data outside of the measurements you've already taken. You've only taken 11 measurements so far, or samples. You're not seeing all the variation yet. So we have to assume that it's wider, and we're going to predict out that way. And that's why the lines get wider as the degrees of freedom get smaller. And so here in the p-value area, what it shows is if we've got only 10 degrees of freedom, that p-value area is going to be pretty large. But as we reduce that down, and you have 20 degrees of freedom, that section is going to be a little bit smaller. So that's going to be a smaller probability. And then if we have up to 30 degrees of freedom, now we have a much smaller area because we have more data and it's going to be more accurate. So they don't need to adjust as much. So hopefully that helps you understand the difference between a t-distribution and a normal distribution.